Okay, let me present this this lecture on some classification models. Okay, and so this is content coming from Chapter 4 in the textbook Introduction to Statistical Learning. And I'll also cover how to do some of these models in using the Tidy Models package. So just a quick overview of what we'll look in this chapter today. We'll just talk about what classification is, and first we'll look at logistic regression, and then we'll also look at linear discriminant analysis. So let's go ahead and take a look. So classification is a method that we use when the response variable is a categorical variable, or we might say it's a qualitative variable. And what we're trying to do is we're trying to predict what kind of category or class or group an observation belongs to. And sometimes that classification prediction, we can put probabilities associated to it. So your answer is not just that it's category A, but we can say we are, there's a 70% probability or a 70% level of confidence, or a score of 70% related to category A, okay, and a 30% that it's not. And so we'll see logistic regression and linear discriminant analysis, and I'll just touch on k-nearest neighbors. Okay, and then a couple other methods that also exist. We have generalized additive models and tree-based models. Support vector machines, those also exist. Okay, the data set that we'll take a look at that's available in the textbook is a simulated data set on credit default, and it's important to note that it's simulated because it's just a touch too clean, or maybe not just a touch. It's too clean for as compared to, say, real life data. And the idea here is it simulates people who have credit cards and people who default on their credit card payment. And default in this case is a bad thing. It means they did not make the monthly minimum payment. And for a credit card company, that's a bad thing. So, a bank, the bank's business model is that they lend out money, and they expect to, basically they give money to people and they say, we're going to give you this money, but you got to pay us back. And when you pay us back, you got to pay it with interest, and that's how they make their money. But if they give money to somebody and that person doesn't pay them back, then the bank loses money. And so to discourage this, they have all kinds of penalties, and they say, if you don't pay us back, then we're gonna ruin your credit score and things like that. But ultimately, a lot of times banks don't recover their money. If a borrower declares bankruptcy or something, the banks who lent to the money, they lose, they're out of money and things like that. So anyway, this is a simulated data set, just saying like, okay, these are the people who ended up defaulting, and we want to see if we can kind of detect that. Okay, and so the response is a categorical variable, whether they defaulted yes or no. And we're going to look at two input variables. The input variables are numeric. We have annual income and monthly credit card balance. Okay, now overall in this data set, the overall rate of default is only around 3%. Okay, and what we'll show you in the next plot is we're going to kind of downsample individuals who did not default. And what downsampling means is that we don't show every single individual who did not default, because that's just kind of like too many people, and it would make the plot a little bit harder to read. And so, there's a few ways to downsample, but in this case, we're downsampling so that both categories kind of appear with similar counts. So let's say there were 1,000 people total in our data set, 30 of them defaulted. Okay, rather than showing you 970 people who didn't default, we're going to just kind of randomly sample only, say, 30 out of the 970 people. So you're going to have, like 30 people who defaulted, 30 people who didn't default. That's what it means to downsample. And so here here's the data set. We have those who defaulted with the little plus signs, and those who did not default in the blue dots. So I don't know, let's say, there might have been, 10,000 people in the original data. I forget how many. And, however many, we have approximately similar numbers of people who have defaulted and those who haven't defaulted. And so, there seems to be a pretty kind of clear relationship that as balance increases, the probability that someone defaults also increases. And how much does income play a role? It's a little bit harder to read in this data set. Okay. We can also make a few box plots. Okay. And the first is going to show a distribution of balance as split by default. And this box plot is going to show a very kind of pronounced relationship between the two variables. So, if I show you this one on the left, we can look at the box plot for balance for those who did not default and those who did. And we can see, as far as those who did default, their balance, their median was around 1,700. Their IQR goes from around 1,500 to 2,000, so around 500. And this is kind of the values. For those who didn't default, their balance is much lower. Their box, the entire box is over here. Okay, so we can see that for those that default, the balance tends to be much higher. And there's kind of this very strong difference between the two groups. And again, this is kind of an overly exaggerated example that, again, this is a simulated data set. So in real life, I wouldn't say it's this obvious, but this is just kind of for a teaching example. The second box plot, the box plot on the right on the slide, shows the distribution of income split by whether they defaulted or not. And when we look at this, there's not as much of a difference, right? Those that defaulted, those that didn't default. The median for those that defaulted, their income's a little bit lower. The median income for those that did not default is a little bit higher. But overall, their Q3 locations are similar. Their Q1 locations are a little bit different, but not dramatically so. Their min and max, there's just kind of less range on the group that did default. But overall, this is, these two box plots don't exhibit as much of a difference as these two box plots when we looked at the balance here. Okay, and so what we want to do is we want to fit a model. And you might wonder, like, as far as classification goes or something, why can't we just use, say, linear regression, all right? So here's kind of another example. And let's say we wanted to predict the medical condition of a patient in the emergency room based on the symptoms. And we'll say there's three possible diagnoses: stroke, drug overdose, or epileptic seizure. And we might have to encode these values as some kind of numeric response. And if we say 1 is stroke, 2 is drug overdose, and 3 is an epileptic seizure, okay, then coding these as numeric and then trying to fit linear regression is going to make our outcomes there's an ordering in our outcomes. And basically the ordering here says drug overdose is somewhere in between stroke and epileptic seizure. And the other thing that kind of goes along here, which that first statement doesn't quite make sense, although I suppose somebody could argue for something like that. But we're also saying the difference, okay? The difference between stroke and drug overdose is, there's a difference of 1. 2 minus 1 is 1, is the same as the difference between a drug overdose and an epileptic seizure. 3 minus 2 is also 1. And that kind of statement just doesn't make sense. And to try to treat something that is categorical as a numeric thing just doesn't really work, okay? Even if you only have, say, 2 responses, okay, and you code one as a 0 and the other as a 1, okay, it's linear regression by by its very nature produces a line, which means it will extend above 1 and extend below 0. You'll get negative numbers, right? And that doesn't quite have an interpretation, right? Here we kind of switch the order. 1 is epileptic seizure, 2 is stroke, and 3 is a drug overdose. And again, this would indicate stroke is something in between epileptic seizure and drug overdose. And again, this doesn't quite make sense either, right? And so if you have these nominal outcomes, nominal means there's no natural ordering, it doesn't make sense to try to make categories into numbers, as the numbers always just have an implicit ordering, okay? Now, numeric coding could work for ordinal outcomes where there is a natural ordering, like small, medium, large, or ratings on a hotel ratings or something like that, where you go from 1, 2, 3, 4, or 5 stars or something like that. One could argue there is you can convert those to numbers. But again, is the distance between a 1 and a 2 and a 2 and a 3 the same? Maybe, maybe not. But that would be kind of one of the, side effects of trying to encode something like that into being numeric. Okay, and encoding something as a 0 or 1 could work if there's only 2 categories. That's what we end up doing for logistic regression. But again, if you fit linear regression, the line would extend to be above 1 and the line would extend to be below 0. Okay. So what we're going to do is we are going to fit logistic regression to our credit card default data. And we're going to look at the relationship between credit card balance and the probability of a default. All right. So we want to say, all right, the probability of default given balance, and this needs to be, produce some kind of probability. And so, we're going to abbreviate this to a function, P of balance, because that's really the number that we're going to kind of mess around with. And we want this P of balance, probability of balance, based on the balance, to be a number between 0 and 1. So probability of defaulting based on the balance. And so we might predict that someone's going to default if the probability of defaulting based on the balance is greater than 50% or 0.5. A bank might choose, some kind of threshold, and they'll say, hey, we're not going to approve a credit card for this person if their probability of defaulting based on the balance is, say, over 10% or something, right? They might have some other arbitrary cutoff line and say, oh, this person is too risky to lend money to, so we are not going to extend a line of credit to this person. Okay. Here, this is a plot, and each of the different kind of values show up as these tiny little vertical tick lines. Okay, and so just at different balances, okay, you can see these tiny little vertical lines. Whoops. And it's the same set of vertical lines on the right as it is on the left. Okay, and on the bottom there's just so many vertical lines that they all kind of merged into just one big blended bar. On the left-hand side of this is a linear regression line. Okay, and this is going to draw a straight line. And again, it gets negative, kind of indicating our negative probability of default, and this kind of extends somewhere, and eventually it crosses to being over 1, and that's just not kind of ideal here. The logistic function, what that does is it converts basically a range that goes from negative infinity to positive infinity to a range that goes from 0 to 1. And so we can see the probability that someone defaults is close to 0, or just right around 0, if, say, the balance is pretty low, between 0 and, say, 1,000 or something like that. and then it climbs up, and we get a higher and higher and higher probability of default, and it would be kind of asymptotic, and eventually, at some point, the probability of default is going to reach +1, indicating that this person's for sure going to default. Okay. If we fit a linear model for one variable, it would look something like this. It would be, the intercept plus slope times x. And, this being a linear function can go anywhere from -infinity to +infinity. Certainly values greater than 1. Whereas the logistic function takes that linear component, the intercept plus the slope times x, and throws it into an exponential function in the numerator, and it's divided by 1 plus the exponential function in the denominator. And so let's say we put in x is a very negative value, okay? If x is a very negative value, then you have e to the, say, like -1000. and that's going to be something pretty much close to 0, pretty much 0. And that would be divided by 1 plus e to the -1000. Basically 0 divided by 1 plus 0, okay? So that probability is going to evaluate to 0. Let's say you plug in +1000, okay? And you have e to the 1000 divided by 1 plus e to the 1000, okay? E to the 1000 is a really big number, right? I don't know, in the billions, okay? So let's just say the numerator ends up being 10 billion, whatever it is, okay? And then we're going to divide by 1 plus 10 billion, right? And so that number is pretty much 1, right? It's a billion divided by a billion 1. That's going to give us a ratio that's very close to 1. And so this basically, as we plug in a value from, say, -infinity to +infinity, the range of the logistic function goes from 0 to +1, okay? There's also an inverse function, and this is the logit function. It's also called the log odds. And this is kind of the inverse of the logistic function. Basically, you plug in a value that's between 0 and 1, and it will output, output kind of the original value. And so if this is how we calculate, the probability, if we plug that back into here and we say, hey, the output of this thing gave me, say, a 95% probability. If I do log of 0.95 divided by 1 minus 0.95, so 0.95 divided by 0.05, so I guess that's what, 20, or 20, no, not 24, 19, okay? That will give us the result of this this equation, log of 19, okay? And this is kind of how we interpret logistic regression coefficients, because when we look at logistic regression coefficients, we have the intercept plus the slope. And so for linear regression, we say our prediction, if we add 1 to x, our prediction changes by b1. And here we're saying if I add 1 to x, the log odds increase by b1. Okay, now the log odds are a bit of a weird thing, but let me try to explain how log odds works. Okay, so first of all, log odds is weird. Okay, probabilities generally a lot easier to understand, and odds are kind of understandable. Log odds really only makes sense in kind of this hypothetical, talking about it situation. No one really, I would say no one's brain really thinks in log odds, but I think I might be able to talk about odds, okay? So we can say, I think understanding a 5 percentage point change in probability is easy to understand, okay? So let's say the original probability of an event is, say, 20%, okay? So that's like a 1 in 5 chance of something happening. And then let's say, I don't know, you want to know, what's the probability of something succeeding? Right now it's 20%. So that's like a 1 in 5 chance of it succeeding. And then we'll say, okay, but if you, I don't know, stretch before doing your exercise, okay, your probability of success jumps up 5 percentage points. And so you go from 20% chance of success to 25% chance of success. So that's easy, okay? If we convert the probabilities to odds, then we can talk about how how there's a change in odds, okay? So we could say a 20% probability, okay? The way you calculate odds is you do probability of success divided by probability of failure, okay? So in a 20% probability of success is going to give us 1 to 4 odds. You do 20% probability of success divided by the probability of failure is going to be 80%. So 0.2 divided by 0.8 is 0.25, or you kind of reduce the fraction and you get 1 to 4 odds. 1 to 4 odds. And so a lot of times in gambling, if you go to say Vegas or something, they don't really tell you the probability of winning the game. They'll give you the odds of winning or something, okay? A 25% probability of success, to convert that to odds, you would say, okay, 25% probability of success divided by 75% probability of failure, 0.25 divided by 0.75, that's going to be basically 1 to 3 odds, or 0.33. So the change in odds is going to go from 0.25 to 0.33, or we have a change in odds of 0.0833. Okay, so adding 5 percentage points to our probability of success, going from 20% to 25%, increased our odds by 0.0833. Okay, here's the interesting thing about odds, though, or changes in probability, is that where you are in the number line will dramatically change your odds. So let's say the current probability of success is 90%. You're kind of following a lot of these best practices or whatever, and we say, okay, right now your probability of success is 90%. Okay, we can say, all right, what would happen if I add 5 percentage points to my probability of success? Well, that's easy. We go from 90% probability of success to 95% probability of success. Okay, how do the odds change? Okay, a 90% probability of success is 0.9, okay? And so the odds there would be 0.9 divided by the probability of failure, which is only 10%, 1 minus 0.9. So we have 0.9 divided by 0.1. That gives me odds of 9, or 9 to 1 odds, 9 to 1 odds. A 95% probability of success, however, to calculate the odds, we would do 0.95 divided by 0.05. 0.95 divided by 0.05 gives me 19, all right, or 19 to 1 odds. So adding that same 5 percentage points, going from 90% chance of success to 95% chance of success, increases my odds by 10, okay? So the relationship between odds and probabilities is not going to be a linear function. Adding 5% back here went from 20% probability to 25%, but it changed my odds from 1 in 4 to 1 in 3, or 0.25 to 0.33. Here, going from 90% to 95% changed my odds from 9 to 19, or I increased my odds by 10 points here, 10. And so the relationship between odds and probabilities is not linear. The logit function basically shows the relationship to the log of the odds function, which turns basically, when you take the log of it, it turns additive relationships into multiplication things. Okay, when you add logs, you're basically multiplying the underlying thing. All right. When it comes time, and I guess, I didn't put this in the slides, but going from, say, 99% probability of success to 99.9% probability of success is basically you're increasing the odds. 99% probability of success is basically 0.99 divided by 0.01. You have odds of 99 to 1, okay? And then 99.9% probability of success is basically 0.999 divided by 0.001, basically 999 odds. So going from 99% to 99.9%, you've increased your odds by, around 900. Basically, pretty close to 100 to 1 to 1,000 to 1. Okay, 101 odds to 1,001 odds are basically one failure out of 100 to one failure out of 1,000. Okay, which is quite a different tale, right? And going say from 99.9 to 99.99, that's one failure in 1,000 to one failure in 10,000, and your odds is basically going from 99 to 999 to 9,999, and your odds are just increasing dramatically by just tiny fractional improvements, going from 99% success to 99.9% success to 99.99% success. And certain industries, say like the airline industry, operates at like 99.999999, some very, very, very high rate of success, that failures are just truly unacceptable in certain industries. Okay, and the difference between 99% success and 99.99999% success is huge. It's a huge, huge, huge difference. And in those cases, to reflect that kind of change, odds would be a more appropriate way to kind of express that, because the differences there might not be so apparent when you're just using probabilities. Okay, so anyway, as far as estimating the coefficients for logistic regression, we do that via maximum likelihood estimation. Usually we just ask the computer and we say, hey, figure out what this is going to be. And so basically what the computer does is it tries to figure out what the probability of X is for kind of every kind of given data point in a particular set of coefficients, beta 0 and beta 1, and we're looking for what are the coefficients that will maximize the product of all of the likelihood probabilities. Okay, and basically it's going to try to the way it does this is it balances two things. It says, okay, what observations defaulted or basically had an outcome variable of 1, and which observations did not default, or which ones had an outcome variable of 0. And it's going to try to maximize the probability for the ones that had an outcome of 1, and try to basically minimize the probability or maximize 1 minus p of x for all the outcomes that didn't default. Okay, we're not going to bother doing the calculations or anything. We don't have to. We can just ask the computer to do this. So if you wanted to fit a logistic regression model on the computer, you would use the function GLM, okay? And so, for this, I'll load up the library ISLR, which contains a data set, and the data set on the credit card default is called default. And we create a generalized linear model. I'm going to store this into the object name model, and we're going to just say, hey, let's model the probability of default based on the balance. So we're going to do default tilde balance. The data comes from the default thing. And then to make it a logistic regression model, we have to use this link function. We'll say family is equal to binomial. And basically what this means is that the probabilities are, the residuals will be modeled as from a binomial distribution. Okay, and here we get two coefficients. Basically, negative 10, 1.065 times e to the 01, so basically negative 10.65 as my intercept, and then the balance is basically 5.5 times 10 to the minus 3, so 0.0055 as my balance, and these are both very highly significant. I get z-scores of negative 29 and positive 25, where we're saying, things look significant when they're more than 2 standard errors away from the mean. And here we're like 30 and 25 standard errors away from the mean, which is kind of ridiculous, but there we go. Both of these things are indeed significant. Okay, and we can go through and you can kind of evaluate all of this, but here's kind of just the summary if you fit GLM. All right, let me show you how we would go and fit a logistic regression model with tidy models. So here I've loaded up library tidy models, okay, and it gets loaded up here. And then I create a logistic regression specification. So I call logistic_regression, parentheses, and that uses Parsnip's logistic regression specification. And then I say, hey, the engine I want to use is GLM. That's one of the available engines for logistic regression. And we'll store this as our logistic model object. And then again, in tidy models, we need to, we take our model and we fit it to our data. And again, right now, I'm not bothering with the whole process of taking our data, splitting it, doing an initial split of training and testing. I'm also skipping, creating folds of our data with v-fold cross-validation or anything like that. Right now, we're just going to say, here's the data I have, and I want to fit a model to all of the available data. And so we're just going to say logistic _mod for the model specification, and we're going to call fit on the data that we have available. And here, when we call fit, we provided a formula, and we're going to do default tilde balance, where the data is default. Okay. Again, when you're doing, say, your Kaggle competition, you're going to go through the process of, setting up v-fold cross-validation. You'll probably set up a recipe. You'll probably set up a workflow, and you'll add your recipe and your model. And here we're just this is just kind of like the quick process. We have our model specified, and we want to fit it to our data. And so there we go. And that's going to give me my logistic fit thing. I'm going to just store that into the arbitrary name logistic_fit. And we can say, all right, what is the resulting fit here? Okay. And it gives us a little summary. It says, okay, your coefficients, your intercept is negative 10.65. And then the coefficient for balance is 0.005499, which is exactly the same values that I got when I fit GLM over here. And of course, it's going to be the exact same results because we used the exact same engine. Here we use GLM, and in our model specification, we use GLM. So of course, we're going to get the exact same results, but here we can see it indeed. In our Parsnip model object, we get the exact same results. If you want that summary table, you can get it too. You just call tidy on the resulting fit, right? And so tidy, we get negative 10.7, 0.00550. The default behavior of tidy is to show 3 significant figures, and so that's why it's rounding it off to negative 10.7 and 0.00550. But if you want more significant figures, you can specify that. Okay, you can specify those arguments there. Okay, your standard error, we get 0.361 and 0.000220. Again, same values that show up in the summary table over here. So these are the exact same values, negative 29.49, 24.95. Here, the p-values are just, less than 10 to the minus 16. And when we come over here, we have the same z statistics, but we get, more precise. So 3.6 times 10 to the negative 191 and 1.98 times 10 to the negative 137. So here we get, three significant digits for each of these things. And again, this is just the results of fitting tidy models. And, you can get the summary table by calling tidy on the resulting fitted object. Okay. And so let's talk about that resulting coefficient for balance, right? Basically, this kind of the quote-unquote slope for this is 0.00550, okay? So what does that mean, okay? This means that when we increase the balance by 1, okay, 1 unit, so basically if there's 2 people and one person's balance is $1 higher than the other person's balance, that results in an increase of log odds of the log odds of default by 0.0055, okay? So what does that mean? Okay, I wrote the exact interpretation of this value, 0.0055, is kind of hard, but one thing to note is that this coefficient is positive. So what that means is that as the balance goes up, the probability of default also goes up because it is positive, right? If it were negative, we're going to say as x goes up, the probability of y decreases, okay? It says the summary table of the logistic regression fit, okay, which we have here, includes a z-statistic and p-value. And both of these things are the result of, like, if you do a hypothesis test to see if this coefficient significant, and the answer is certainly yes. We would reject the null hypothesis because our p-values are so tiny. If the p-values, on the other hand, if you do another analysis and the p-value ends up not significant, okay, then that would indicate that the results observed in your data could be a result of just random chance, okay, and that any observed difference in the probability of some kind of outcome that we see in our data, that could just be coincidence, okay. All right, let me show you what kinds of results you can get, all right. So here we can use this in tidy models, okay. I can take the fitted object that we have, logistic fit, okay, and I'm going to say make a prediction, okay. I'm going to say predict logistic fit. You have to provide it a data frame with your new balance, and so I'm going to say new data is data frame, and our predictor variable is balance. I'm going to say 1200, okay, and when I put in 1200, it says your predicted class is no, meaning we predict that it's not going to default, okay. One thing you can do is when you have something like a logistic regression fit, you can change the type of prediction to, say, a probability. And so I can say, hey, what is the probability of defaulting when the balance is 1200? Okay, so here it says my prediction, prediction no, the probability of defaulting is 98% no, and 0.017% yes, or probability 0.017, so around a little under 2%, 1.7% yes of defaulting. Okay, if that balance goes up to 2000, then the probability of defaulting goes up to 0.586. Okay, probability of no drops down. Okay, these two numbers just add up to 1 every single time. And if the balance goes up to, say, 2500, and we say make a prediction, the probability of defaulting is now 0.957. Okay, so we can see it goes from 0.017 to 0.586 to 0.957, going from 1200 to 2000 to 2500 there. We can create a confusion matrix, okay, of the available training data. What a confusion matrix shows is it says, hey, what did you predict and what was the actual result? So we can go through all of the data available to us, and we can say, all right, based on the balance, this is my prediction for whether the person defaulted or did not default. And then this is what the data shows, that they actually did default or did not default, okay? So to do this, we're going to take the entire data set, default, okay? And I'm going to select just the column of whether they did default or didn't default. And we're going to call that the truth. That's going to be the truth column, okay? And then, and I'm going to bind that to the results of calling predictions. So my predictions, I'm going to take my logistic fit model, and then I'm going to say, I want you to make predictions where my new data is basically the default data set without the outcome variable of whether they defaulted or not. So basically just kind of, in our case, it'll just use the balance info, but it does basically have all of the other variables available, but here it's just making predictions based on the balance. And so we'll take those results, and basically we'll have two columns. One column will be truth of whether they actually defaulted or did not, yes or no. And then we're going to have our predictions. And remember, if you just call predictions without, and you don't say type equals probability, then down the response, you'll just get a bunch of either no's or yeses, the no's or yeses, okay? And then we can call this function confusion matrix, okay? We say, hey, the confusion matrix comes from default underscore predictions, which is just our two columns of whether the person defaulted or not. And the two columns are the true values of yes or no, they defaulted. And then we have a column of dot predictions or dot predicted class, which will be yes or no's. And so what we see is that when we predicted they weren't going to default, they did not default 9,625 times, and yet they did default 233 times, okay? And when we predicted that, yes, they would default, okay, 42 of those people did not default, and 100 of them did default as we predicted. So this is our result, okay? And so we can say, well, what is our overall accuracy? So the way accuracy is calculated is basically we say, okay, well, how many observations total? I think there's 10,000 observations, but let me just do 9,625 plus 2,233 plus 42 plus 100. Okay, so we have a total of 10,000 observations. How many of them were correct? Well, we were correct for the 9,625 times where we predicted no and the truth was no. And we were correct for the 100 times where the truth was yes and we predicted yes. Okay, so we were correct 9,725 times divided by 10,000 observations total. And so our probability of success or accuracy is 0.9725, which is what we have here. Our accuracy or binary accuracy there is that, okay? There is, so that's just the total correct divided by the total predicted. You just call accuracy there, okay? Another measure that we can use is the Matthews correlation coefficient, also known as the phi coefficient, and I'll take us to the Wikipedia page on this, okay? And this is kind of how it's calculated, right? So basically, plus 1 indicates perfect agreement, -1 indicates perfect disagreement, and 0 indicates no better than random prediction, okay? So we're getting a score of 0.449, which means sometimes we're right, but not always, okay? And you know, we can see, yeah, there were quite a few times where we didn't think they would default, okay? Our answer was no, but they actually ended up defaulting 233 times. And if you look at those who did default, okay, there were a total of 333 people who actually did default, and we only predicted basically 100 of them, okay? We only predicted basically 100 out of 333 people who actually did default. We didn't get them all, okay? So that's, you know, as far as those who didn't default, we did pretty good, okay? So there were a total of 9,625 plus 42, 9,667 people who did not default, and we were right 9,625 times. So if I do 9625 divided by 9667, you know, we're getting like 0.9956% accuracy, okay? But as far as those that did default, right, there were a total of 333, and we only got it right 100 out of 333 times. And so, you know, that's a probability of success of only around 0.3, okay? So, um, so the MCC is kind of a a value in between 0.33 and 99.5%. Okay, and the way it's calculated is you take basically you multiply the product of when you get it right, you subtract off the ones you get it wrong, and you take the square root of the product of all of these things. So that's it has all of these kinds of ways to go about calculating. Okay. There's another measure. Okay. One is called the F score. Okay, or the F measure. All right. And here, you want to kind of get you want to talk about kind of your event of interest here. And so let's get into this, right? And so for here, we take kind of our results and we say, our predicted class is that, and our event level, that's the first one. So this is kind of our F score, and it's calculated as this. It says it's the harmonic mean of precision and recall. All right, precision is basically how many things are true positives, and you divide by your total number of retrieved elements. Okay, this is kind of known as your sensitivity. Basically, like how often did you detect that somebody is actually going? I guess in our case, no being the event of interest, will not default. How many people will correctly kind of pay things back, okay, out of everybody that you identified as no. And then and recall is basically how many true positives out of everyone that actually is so how many did you identify as true positives, okay, correctly identified as positives, divided by everyone that should have been identified. That's going to be your recall, okay. And so that gives us your F score, 0.986. Okay, if you switch this, okay, and so this is saying getting the no measure, correctly identifying the no's is more important. Hey, we did pretty good, okay, because remember, when the truth was a no, we got it right most of the time, okay. If we say, hey, detecting when somebody defaults, that's more important, okay? The yes default, okay, is the event of interest. So here the event level that we should be scoring on is the second entry. First and second is determined by alphabetical order. So no comes first, yes comes second, okay? And so in this case, when we said the yeses are more important, we score much more poorly, okay? The F measure is only 0.421. And that's, again, because as far as those who actually defaulted, there were 333 of them, and we only got it right 100 times out of 333, okay? We got it right less than half the time, only 30% of the time. And so our F measure there is much worse, okay? Remember, you can, if you're just going straight for accuracy, okay, and you didn't want to spend any time on this model, as soon as you found out that, close to, around 97% don't default, okay, 96.67, you could have just built the simplest classifier and just said, no one's going to default, okay? No one's going to default, put no energy into it, and you would have gotten close to, your accuracy would have been 0.9667, okay? And implementing the model only improves you a tiny bit, 0.972. Okay, but these other measures, would differ drastically, right? It would be kind of like you could have a fraudulent, like, COVID test. Okay, the fraudulent COVID test is just going to be a piece of paper that you dip it in the water and then it always comes back and it says you tested negative. And you know, it'll be, overall it'll score quite accurately because I don't know what percentage of people would test positive at any given moment in time, but if the vast majority of people currently test negative, it's going to be pretty accurate in that it's going to get a lot of true negatives correctly. But of course, it will never actually have a positive result. It's a completely worthless test, but you're going to get pretty high accuracy. So other measures like the F measure that kind of takes into account kind of both the yeses and the nos, and you decide which one of these things is more important. This is a way to measure that. Okay, so you have precision and recall. And that emphasizes whichever one's the event of interest would you specify here. Okay, so again, precision is the true positives divided by all of the retrieved elements, everything that got identified as being positive. So the true positives plus the false positives. Okay, plus and the recall is the true positives divided by all of the relevant elements, all of the things that should have been identified, right? So everybody who actually is, let's say a yes, okay, actually somebody who is going to default, okay, we have basically the 100 people. So here our recall was like 30% because we had 100 people who actually were identified as going to default, but we had a whole bunch of false negatives. We had 233 people that actually defaulted, but we predicted no. Okay, so that's everybody over here. Our precision, okay, is how many we identified divided by basically everybody that we selected. So that would have been 100 divided by 142. So let's see, I don't know what a harmonic mean is. So we have 100 divided by 142, so 0.704 for our precision. So 100 divided by 142, what is that? 0.704. 0.704. And then my recall is 100 divided by 333, so that's 0.300. Okay, so my recall is 100 divided by 333, so that's what, 0.300. Okay, and so how do we calculate the harmonic mean? I feel like this is a meme at some point. Okay, so the harmonic mean is 2 times precision times recall divided by precision plus recall. So what is that? 0.704 times 0.3 divided by 0.704 plus 3. And we're going to multiply the... let's throw this into Google here. Does that give me 0.4207? Is that what we got? Okay, 0.421 for our F measure here. So, yes, we have correctly reproduced the result there. Okay, so we have precision and recall. Okay, so all right. Oh, okay. So let's do logistic regression where we have a categorical predictor. So in the data set for default, credit card default, there's a categorical variable on whether the person is a student or not. Okay, so we have student, yes, and so here we have a coefficient of 0.404, indicating that if the person is a student, they are more likely to default than if the person is not a student. Okay, so so that was done by doing make a GLM model default based on student. We use our default data set. Logistic regression, we'll call the summary on this. Okay, and all right, and so here we would go about doing this in tidy models. Again, we specify our model, logistic regression, set it in GLM, so that's exactly the same as before. And now we're going to just, again, fit it on all of the available training data. So we'll say default as predicted by student. Okay, and then here I just say, hey, give me the coefficients from the, we throw it into tidy, the results of making the predictions, throw that into tidy, and we get the same estimate, right? 0.405, a positive thing. We have a p-value of practically, we have a p-value of 0.0004, indicating that it is significant. The intercept, on the other hand, we have a p-value of practically 0, negative 49.6 for a statistic there. Okay. So how does this work? All right. So here we fit a logistic regression model with a categorical predictor, student, which takes on the values yes or no. Okay. And kind of like in multiple linear regression, what R does is it uses dummy variable coding for each of the categories. Okay. Minus one in the categories. So this basically means student yes is coded as 1 and 0 for everything else, student no. And the coefficient here is 0.4049. And it being positive means that a student has a higher rate of default than non-students. And so, if we say, hey, make a prediction, give me the probabilities, we can see, the change is only a little bit. But basically, if the person is a student, their probability of default is 0.0431. Whereas if the person is not a student, their probability of defaulting is lower at 0.0292. Okay, but that difference is significant, and it indicates that yes, students do have a higher rate of defaulting, 0.043 versus 0.0292. Okay, so that's what we have here, right? We can also do multiple logistic regression. So not just one predictor, but multiple predictors, right? So similar to linear regression, where you have multiple predictor variables, here we can have multiple predictor variables for logistic regression. Same kind of idea here. It's just that now you are putting in multiple variables. You have this basically a linear equation, but it goes into the logistic function. So you have e to the whatever that linear equation is, divided by 1 plus e to that linear equation, okay? Again, maximum likelihood estimation. So here, I'm going to throw in all 3 of our variables, I think, in the default data set. So we have the balance, which is numeric. We have the income of the person, which is numeric. And then we have, is the person a student, yes or no? And so, so we throw that into here. We get basically a positive coefficient for balance, positive thing for income, but it is not statistically significant. And then we have the student, okay, we have a significant thing, but notice this, we have a negative coefficient now, okay? Whereas when we did student back here, the coefficient was positive. We said if someone's a student, they're more likely to default. But over here, if somebody is a student yes, now our coefficient is negative. So what's going on here? Okay, and yeah, so here I do it with tidy models. Same things. Create our logistic regression specification. We fit it, okay, to our data, calling fit. And then I'm going to just ask for to tidy up our results, okay? So, and again, here we get our tidied up results. We get a positive coefficient for balance, a p-value that is not significant for income, and then we get a negative coefficient for student yes, okay? Okay, so, for this kind of credit default data, all right, we see that the coefficient for balance is still significant and still positive, indicating that a larger balance is associated with a higher probability of default. Coefficient for income is not significant, indicates that any difference in probability of default for those with higher or lower incomes could just be explained away with random chance. And then finally, we see that the coefficient for student yes is negative and significant. And so this seems to be in conflict with the logistic regression performed earlier, where the coefficient of student ES was positive and significant, okay? So what this means is that if we keep the variables balance and income fixed, then a student is less likely to default than a non-student who has the same balance and income. And we can kind of plot this, right? So on the left, we can see that for a given credit card balance, in blue, we have those who are not students, and in orange or brown, we have those who are students. And we can see that when we plot these two things, that the rate of default for those who are students in brown is lower than the rate of default for those who are non-students, shown in blue, okay, for the same levels of default, okay? But what we see on the right is that in general, okay, if we look at student status and the credit card balance, in general, students have a larger credit card balance, okay? And because larger credit card balances are associated with higher rates of default, okay, the overall rate of default for students is higher than the overall rate of default for non-students, okay? But if you hold the balance constant, then the rate of default for students is lower than that of non-students, okay? And that's what this relationship reveals here. Okay, so that's that for logistic regression. Let's look at another classifier model, and this is we can call this linear discriminant analysis. It's also just a form of the Bayes classifier. Okay, the Bayes classifier is basically based on the based on the data, you can make a distribution of X for each of the different classes of Y. Okay. That is, you can estimate the probability of X given Y is equal to some class, right? And to try to, we can use Bayes' rule, okay? Because what we want to know is what is the probability that this observation belongs to some class K if we have some value for X, okay? If X is equal to some value X here, what is the probability that Y belongs to some distribution K? And so this is found by doing, what's the probability of A given B? And we'll use Bayes' rule and we'll say, what's the probability of B given A times the probability of A divided by the probability of B? Okay. So the way this would work with Bayes' theorem, if we're trying to say, all right, what is the probability that some observation belongs to class K if its X value is this number? We'd say, okay, well, what's the distribution of X, okay, given that it belongs to K, right? So this is basically the PDF of X for an observation if we say it comes from class K. So basically we have to make some assumptions about the form of the PDF, okay, the density for that particular thing, okay? Probability of Y equals K is just kind of the prior probability that an observation comes from class K in the first place. And, you often figure this out by just kind of taking how many observations were in class K divided by the total number of observations. And then the bottom is the marginal probability. It's the probability of getting that observed value of X regardless of the cases. And the way you do that is you just calculate the numerator for all of the different possible cases and you add them all up, okay? Okay, so I'm going to abbreviate just to kind of save some time. We're going to abbreviate the probability that Y is equal to K given X as just the probability sub K of X, all right? And that's going to be given by, determined by basically the PDF, all right? So we've got the probability that K of getting class K, if it belongs to X, we'll have the PDF of getting PDF of X for class K times the prior probability of belonging to class K, and then we add that up across all of the different possible classes here. So if we just have one predictor, okay, we'll start with just a simple assumption, and we'll just say, hey, you know what? Our X variable follows a normal distribution, okay? And if you don't want to have it follow a normal distribution, then that's fine. It's not going to be linear discriminant analysis, but it'll still be the Bayes classifier, and you just use a different PDF here, okay? But linear discriminant analysis assumes a Gaussian distribution and uses is the Bayes classifier for that. If you don't want a normal distribution, it's still the Bayes classifier, just it's technically not linear discriminant analysis. Okay. All right, so the distribution, our PDF is going to be the normal distribution, which is basically, we've calculated in R using the function dnorm. That gives us the PDF, okay, the PDF of the thing, and we just give it kind of our current X value, and we'll need to know, hey, what is the mean and what's the standard deviation? In linear discriminant analysis, we assume sigma is the same for all of the different classes of K. In some other forms, you can relax that assumption, but basically we're just assuming different groups have different means, okay, and that's, we're going to plug in the different mean for the different groups, but we'll plug in the kind of the same sigma here. And then we have kind of our prior probabilities. So we have our prior probability multiplied by basically dnorm, and then we'll do this for all of the different classes, add them up, that will form our denominator, okay? If you take the log of this whole function, do a little bit of rearranging some terms, basically this overall kind of sigma that you would find is basically going to be this is not sigma, this is delta, okay, is going to be x times mu sub k divided by sigma squared minus mu sub k squared over 2 sigma squared plus the log of all of this. And basically you would just choose kind of the delta k that ends up being the largest. Let's just try out a simple example, okay? Here I've got two normal distributions. One has a mean of negative 1.25, all right, in green. The other has a mean of positive 1.25, shown in pink, right? And both of these have the same variance of 1, okay? And so this is the Gaussian normal distribution centered at negative 1.25. Here's the normal distribution centered at positive 1.25. And we can see that, hey, if I needed to draw a line that separates these two, I would draw that line right around 0, okay? Right at 0, actually. Theoretically, it would go at 0. How would we go about doing something like this? With our data, we can kind of plot just some simulated data coming from one distribution, data coming from the other distribution, and, we would draw a split here. A couple observations would get misclassified and things like that, but overall, this would kind of split them, right? Let's say both of these observations had prior probabilities, then that would just be, prior to knowing anything, we'd say it's 50% green and 50% pink, or 50% group 1 versus 50% group 2, okay? The hardest part is trying to figure out what the density function should be, all right? It's real easy if you just assume it's normal, okay? If that's a bad assumption, then your classifier is going to have problems. But here's the thing, even if assuming it's normal is a bad assumption, a lot of times it works out, okay? I know that's kind of maybe not the best attitude to have about a lot of these things, but a lot of times in machine learning, you don't worry so much about the mathematical assumptions and whether they are safe or not. The proof is in just the predictions. And if you're making good predictions, then you say, well, it can't be all that bad. And it turns out using the normal distribution as a way to make predictions, it can't be all that bad because a lot of times it's accurate. So, the assumption basically makes everything a lot easier, assuming everything has kind of the same variance because, the only thing you really have to worry about is just figuring out the mean of each class, okay? Estimates for the mean of each class is basically what is the mean of the observations that belong to class K. So you say in your training data, I know these observations are class 1, so I'm just going to take the mean of those, and that's going to be my mean there. And I know these observations are class 2. I'm going to take the mean of those observations. That's going to be my mean for class 2, so on and so forth, okay? The variance of all of these classes is basically going to be the average square distance from the class mean averaged across all of the possible classes. So you say, all right, here is class 1. Let's get basically the mean there. All right, here's class 2. Let's get the mean, basically the variance there. And you're going to get all of these different kind of variance values for the different classes. And you basically kind of do a square, a weighted average of these things. Okay, so you just kind of take square distance, add them up. Obviously, the classes that have more observations will get a larger sum, and then you divide in total by n minus k. It's kind of like n minus 1 for variance, but n minus however many groups you have. And it works very similarly if you want to do it for multi-dimensional data. So you don't have to just have one predictor. Okay, and and so that's how it will work. Okay, and you know, with linear discriminant analysis, we assume that the variance for all of the classes are the same. And now if we have a multivariate Gaussian, we're going to assume the variance covariance matrix is the same for everything. Okay, if you wanted to do this in R, you can use library mass, okay? And you can call LDA, linear discriminant analysis. You're going to say, let's try to classify the outcome variable default based on the balance and student variables. Okay, so again, student is categorical, balance is numeric, and that's going to be our model. And then, and once you do that, that fits it to the data, and then we can say, all right, I want to make predictions based on our data, and then give me what the predictions are. Okay, and so here it says, all right, your predicted values are this, and the true values are this, okay? And so we were correct, 9,644 plus 81. We were wrong, 252 plus 23. We were wrong a total of 2.75%, okay? Seems pretty good, but again, just keep in mind, overall, only 3.33% of people defaulted, right? And so, you know, we're outperforming that a little bit, but not by much. That's our error rate. Okay. How would we do linear discriminant analysis using tidy models? Okay. With tidy models, okay, you would you'd create discrim underscore linear. Okay. And this will create a linear discriminant analysis model. I should say you have to install the library discrim. Okay, and this is just basically a Parsnip extension package for discriminant analysis, right? So Parsnip is kind of this, again, the tool that we have in tidy models that basically translates all of our model specifications into, you know, what other language or package that we want to do, okay? So here we're going to use set engine mass, same thing that we have here. Okay, and you know, how do we make predictions and how do we make confusion matrices? You know, all of these things were all slightly a little bit different. Okay, but tidy models will just kind of unify that. But you do have to kind of extend tidy models or Parsnip by just saying like, hey, use discriminant. So we're going to say discrim underscore linear. That's going to do linear discriminant analysis. We're going to set engine to mass, and then we're going to, once we have our model specified, we'll fit it to our data. And we'll say default as, you know, predict default based on balance and student. Okay, this is the resulting thing, and these are our kind of predictions. All right, or our kind of I'm sorry, these are group means. So prior probabilities, 0.9667 no, 0.033 yes, and then you know, the group means. For balance of those who didn't was 803 and 1747 for yes. For those who didn't, around 29% who didn't default were students, and for those who did default, 38% were students. Okay. All All right, so here we can say, all right, make our predictions, and I want to create a table where basically one column is the truth. So we're going to select just did they default or not, and then here we're going to make predictions based on the fitted data, and we'll say bind columns. Take that column of default, which we labeled the truth, and we'll bind that to our prediction columns. Okay. And now make a confusion matrix. Okay, confusion matrix. The truth is equal to our truth column. The estimate is our dot predicted class, because that's what we get when we call predict. And this is our confusion matrix. 9644, 23, 252, 81. Okay, same exact results. If I scroll back a few slides to the results for mass, and of course it is. Of course it's the same results, because here we use library mass, and then when we use tidy models, we specified set engine mass. So of course, underlying everything, it's R is doing the same calculations. Okay, but this is all in tidy models format, which we like, because it allows us to run a whole bunch of metrics, and a whole bunch of other stuff, kind of in a simple and clean way. So here again, I can create a metric set, all right, and then I can call, ask it to make these calculate the metrics for our data. So here, my metric set, I want the accuracy, I want the MCC, basically the phi coefficient, I want my F score, my F measure, okay, which we've talked about when we did logistic regression. And then once I do that, I'm going to say calculate the classification metrics based on our table of predictions and true values. Okay, and here again, the value of interest is those that actually did default. Okay, that's the second level, because the first level is the no, second level is the yes. So my accuracy, overall accuracy, is 0.972. My MCC score is 0.426. My F measure is 0.371. Okay, so that's what we have. Let me see. Here is, let me scroll back. So let's, we're on page 52. Let me scroll back to what we got when we got logistic regression. Okay, so with logistic regression, my F measure was 0.421, and my MCC was 0.449, and my accuracy was 0.972. I can't remember. 0.449 and 0.421. So my F measure actually went down, and my MCC went down also. So linear discriminant analysis, I would say, doesn't perform as well as the logistic regression. Okay. Again, sensitivity and specificity. Okay, so here, sensitivity is, again, how many times did you correctly identify someone was going to default out of everybody who did default. Okay, and then specificity is basically how many times did you avoid false positives. Okay, how many negative selected elements are truly negative. Okay, so basically everybody that did not default, so everybody who paid on time, did you misidentify and say some of them are going to default, right? Those are the false positives, and basically the specificity is like how frequently did you truly how frequently did you avoid false positives. Okay, sensitivity is how basically your accuracy when it comes to detecting those who truly are going to default, and then specificity is like how accurate are you when it comes to like avoiding false positives. So our sensitivity, not so great. Okay, not so great, because we only identified 81, okay, out of 333, right? So 81. So there were a total of 333 people who truly did default, and we only identified 81 out of them. 81 divided by 333. So our sensitivity is only around 0.243. Okay. We could also call just sensitivity which is a function in tidy models. And it says, oh yeah, your sensitivity score is 0.243. Okay. Specificity, how often did you avoid false positives? Okay. So false positives is basically the truth is they did not default, but we made the mistake of thinking that they would default. So we had 23 false positives, and we're going to divide that. That's our false positive rate. So basically not our false positive rate. So 9644 plus 23. So out of 9,667, we didn't get any, these were not false positive. 9644 divided by 9667, 0.9976. Okay, that's my specificity. All right, and I got 0.998. So 0.9976, that's the number I have. And again, you can get that from tidy models just by calling specificity. Okay. Oh, and here are those calculations here, right there. Now, so as far as the bank goes, okay, lending to someone who defaults will leave the bank with a loss of a potentially large loan. Turning away a potential customer who is deemed risky will lead to a loss of kind of collected interest. But if you're the bank, you may consider it worse to lend money to someone who's default than it is to turn away a potential customer. And so you might be willing to turn away 5 good customers if that means you're going to avoid 1 bad customer that's going to default if you're the bank, okay? So you might actually want to lower, right? Change the threshold of predicting who's going to default by lowering kind of that probability threshold. So kind of, so far our threshold was 50% as far as yes or no, okay? And that led to a sensitivity of only 24%, okay? Basically, there are 333 people who actually defaulted, and we only correctly identified 81 of them. And so we might want to say, hey, you know what? Anybody who has a probability default of over 20%, we're going to just deem too risky. We're not going to wait for it to hit 50%. Okay, and so now we can adjust this threshold. Okay, so we can say, all right, we have the probability of whether they're going to default. Okay, and a lot of these numbers are pretty low, 1%, 2%, less than 1%, things like that. Okay, and so here, our predictions, we can kind of create a factor of basically yes or no, basically taking that prediction probability. All right, so we're going to say, all right, my predictions will have a yes or a no based on basically that column dot predict yes. So we're going to take this probability yes. If that number is over 20%, then we're going to put yes or no, and we got to if else that. Okay, and then we'll bind that to basically our current predictions. All right, and so now I can say, hey, what's my sensitivity? Okay, if instead of using the original predicted class, I use my kind of adjusted predicted class. And if I do that, my sensitivity goes up to 0.586, but my specificity goes down to 0.976. So now I'm getting more false positives. And if you kind of look at the rates here, okay, now out of 333 people, I've correctly flagged 195 of them. Okay, so my sensitivity goes up to 195 out of 333. Sensitivity, a better score of 0.585. Okay, but again, now I'm having more false positives. Okay, because I said, hey, if you're over 20% risk of defaulting, you're too risky, so we're going to turn away. So we're going to end up turning away a lot of kind of people who weren't going to default. All right, so we end up having more false positives. So now my specificity goes down to only 0.9756. Okay, if we increase, all right, if we lower that threshold even further, we say, hey, if you're going to reject anybody with a risk of default 10% or higher, then what happens is my sensitivity goes up to 75%, but now my specificity goes down to 94%. So now I'm flagging more people who default more accurately. I'm getting 75%, getting it right 75% of the time. Okay, but now I'm making a lot more false positives. Okay, my specificity drops down to 0.94. Okay, and so we can kind of see how the relationship of all of this. Okay, in this graph here. Okay, so here I have threshold. So when I have my threshold of say 50%, okay, then my my sensitivity gets lower and lower and lower. Okay, so 1 minus sensitivity, that's this blue line. Okay, and then my specificity, the orange dotted line, okay, is low. Okay, that is kind of my false positive rate. 1 minus my specificity, that's my false positive rate. That's pretty low. Okay, but my 1 minus my sensitivity is also pretty low. My error rate is 1 minus 0.243. Okay, I'm getting it wrong 75% of the time. Okay, but if I brought my threshold down to 20%, okay, at threshold 20%, the error rate is for 1 minus my sensitivity is 0.414, right? So at 20%, my sensitivity is 0.586, and 1 minus that is 0.414. So it goes down. If I lower my threshold even further, I get it right 0.751. I get it wrong 0.249. So that's right here. Okay. And so we can see, but if you draw your threshold to 0, everybody would get rejected. Now you have a really high kind of error rate there. So you can see this dramatically drops off as you increase your threshold. But as you increase your threshold, then your error rate regarding not correctly identifying who's going to default goes up and up and up and up. Okay. We have something called the ROC, Receiver Operating Characteristics Curve. Okay. And that kind of shows all of the possible error rates for different threshold levels. Okay. And the overall performance of a classifier is given by kind of the area under the curve, which we call our AUC. Maximum possible value is 1, and that is achieved if the curve starts at the lower left, goes straight up to the top left corner, where your false positive rate is 0 and your true positive rate is 1, and it cuts across the top to the right corner where you have false positive rate 1, true positive rate 1. Okay, that kind of example is not really possible in real data sets. Okay, a worthless classifier that uses just random guessing will have an AUC of 0.5, and that's just going a diagonal line from the lower left to the upper right corner. Okay, and so for something like this, we have an ROC curve looking kind of like this. And so here we have kind of the false positive rate, which is 1 minus our specificity, and the true positive rate is our sensitivity. And what we saw is when we had, say, a threshold of 0.5, our sensitivity was 0.243, and our false positive rate was 0.003. Okay, as I decreased my threshold of 0.2 resulted in an increase in my sensitivity of 0.586, but my false positive rate did go up to 0.024. If I decreased my threshold further to 0.1, okay, my sensitivity went up to 0.75, but my false positive rate, also went up to 0.06. Okay, and so here I've kind of labeled all of these things. When you draw a regular, just an ROC curve in, say, in R, it's not going to show all of these different labels. It's just going to kind of do this, right? This is how you would calculate this. The ROC curve in tidy models would be found by, you take your kind of predictions, okay? And then you also need a probability because it requires all of these different probabilities here. and then you create the ROC curve, right? You give it the truth, and then your probability of predicted no. That's going to be the group of interest here, and this is going to be the drawing of the ROC curve. Okay, that's what you end up getting. You have another thing is quadratic determinant analysis, similar to LDA. Here, we don't, with QDA, you don't assume all of the things to have similar variance. We allow the variance to be different for each of the classes. And in this case, because you have more parameters to estimate, generally you need more data to make an accurate model. As far as bias variance trade-off goes, LDA would be considered less flexible, so have more bias, less variance. QDA will be on the moved in the other side, more flexible, and will have less bias in the long run, but you'll have more variance depending on the data that you use to train the model. And so, you using one random set versus another random set, you can end up with some pretty different results there. Okay, that is our lecture, our video today on different classification methods. And hopefully this will be useful for the other Kaggle competition, which I'm working on, which will be a classification problem. All right, thanks for tuning in.